Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem again. Problem 101, Symmetric Tree. In this video, we're going to share a treatment based on iterative format. So in the previous video, we explained a solution based on recursion. The reason we first do a recursive solution is due to the fact that binary tree is a recursive abstract data type or data structure. So in this video, we want to review more details. So therefore, we want to share a solution based on iterative format. So this problem statement is very short. So basically, given a binary tree, we want to check if it's a mirror of itself, right? So here are two examples. In example 1, so the return is true, and in example 2, the return is false. So in this problem, the number of nodes in the tree is given by this number, this closed interval, and the values can be negative, can be 0, can be positive, but bounded in absolute value by positive 100. So with that said, so we are ready to do this problem. So for this problem, so a naive solution might be that, I coordinate all the nodes and then use the coordinate to check. For example, if this coordinate is 0, 0, then this coordinate, let's see, so it's negative 1 and 1. So we increment the level by 1, and then if you go to left, you decrement the x coordinate by 1, and if you go to right, you increment the x coordinate by 1. But when we go down, we update the y coordinate. But this way has a problem, because here, if this is 0, 0, so this is negative 1, 1, then we move right, we're going to give 0, 2. But this one is positive 1 and 1. Then you go to left, it also gives you 0, 2. So there are some confusion here. Therefore, we're not going to take that route. So, but that's a typical solution with fault. So in this video here, I'm going to practice the use of deck. So it's a collections object in the Python. So here, so I'm going to first initialize a collections deck. So in order for the convenience of comparison, so I'm going to first initialize the queue like this, and then in the process we want to make sure, so each time we compare two objects. So that's also why we initialize the deck as this. So for example, in example 1, so if we want to compare the left subtree of this 1, so here, then we want the left subtree of 1 and its left corresponding to the right subtree's right, and here the left subtree's right should correspond to right subtree's left, right? So each time we want to compare two objects, so that's why we use this initialization. So next, basically, we want to do this comparison. So actually, if you have reviewed the previous video of recursive solution, basically you can regard this iterative format as a translation of that method. So what we're going to do is first I'm going to check. So here, let's use this length of this queue, because this deck is an iterable, so it has a length we can call this length. So if this length is greater than 1, so what we are going to do? So first I'm going to pop. So I'm going to pop left and pop from the right. So here, let's call it pop left, and then here let's call it pop right. So that's why, because we are using pop twice overall, so we need to make sure the element should be greater than 1, right? So then we want to compare these two subtrees. So the comparison is similar as in the previous video. So first, I'm going to check if not T1 and not T2. So in other words, they're both null, right? Actually, if let's keep write this, because this maybe it's parallel to the stop condition or edge case in the recursive format, but here let's use a continue condition, right? It's continue. So after this check, basically we are facing conditions either T1 or T2 is not null. But now if we check not T1 or not T2, so in this case one of them is null and the other is not null. So in this case, so we're going to return false. So that's another check. So otherwise, so after this two if checks, so we're facing the case that both T1 and T2 are not null trees. Then we can compare the value, right? So if T1 value does not equal to T2 value, so because the way we do the comparison in pop, they are in the corresponding mirror image positions. So if their value should be equal, otherwise they actually will just return false because it's not symmetric. And then after we do this if check, if still nothing has returned, then we want to compare this one, this pair, and this pair, right? So what we are going to do is we append. So here I'm going to, let's regard T1 as here. I'm going to first append T1 right? So let's see, append left T1 right. Then T1 right actually corresponding to T2 left. So here append. So here I'm going to append T2 left. And then we compare this 3 and this 3. So the first 3 corresponding to append left, it's T1 left. And then the second one I will append, just use append from right, that is T2 right. So this T1 is left, so left right corresponding to right left, and left left corresponds to right right. So this is the whole while loop. Afterwards, if nothing has returned, so we're going to return true. So this is a solution format to this problem. So before we make any comments, let's do a check. Yeah, it passes one example. Now let's look at generic case. Yeah, it passes all the cases. So here I would like to see in the first thing in this problem, so naturally I would like to write a solution with recursion. So here is the use of deck, or so here we use this because each time we want to compare a pair of nodes or root values. So we are going to do this kind of initialization, and then we pop twice each time, and append, we append, use 4 append operations from the left and the right directions, each twice. So with that said, I guess that's about it for this easy but interesting problem. And yeah, that's it for this video. Thank you.